Good morning, everyone. My name is Chris Long, and this talk is called Accelerating the Analysis of Offensive Security Techniques Using DetectionLab. This presentation consists of three main parts. I'll first start out by explaining what DetectionLab is and how it came to be. Next, I'll provide an overview of some of the primary tools included in the lab environment. Lastly, we'll dive into some scenarios to show what it looks like to triage and do analysis using DetectionLab. Before I get started, I'll just give a quick introduction. My name is Chris, although everybody just calls me Klung. I'm currently a senior security engineer on the Security Incident Response team at Netflix. However, DetectionLab is a project I work on in my own personal time and is not affiliated with my company. I've previously worked at Palantir, Uber, and Facebook. One fun fact about me: 2年ぐらい日本語を勉強しています。しかも4回日本にいたことがあります。でも、私の日本語能力は発表をするのに十分ではありません。So, I think the first and biggest question to answer as part of this presentation is, what is DetectionLab? DetectionLab is an open source project on GitHub that I created about 2 years ago. The primary idea behind creating DetectionLab was that I wanted to use free and existing tooling to allow people to rapidly and automatically build an Active Directory lab environment. In basic terms, DetectionLab is a repository containing a variety of scripts that allow you to automate the process of building an Active Directory environment complete with logging and security tooling. That's a lot of words, but I think the key word here is automate, and I'll explain more about that on the next slide. DetectionLab isn't a new or novel way to perform analysis. It's about streamlining workflows. One thing that sets DetectionLab apart from similar projects is that it supports deployment on many different platforms and different deployment methods. One thing I realized as a defensive security professional was red teams and pen testers and offensive security professionals are very good at sharing the tooling that they have, and they even have entire Linux distributions such as Kali that exist for their craft. I was a little bit sad that we didn't have something like that as defensive security professionals, so I wanted to build something that would be widely useful for people. Here are some ways DetectionLab could potentially be used. When it comes to things like security tooling, you can never do too much testing to ensure you're collecting the telemetry you expect and detecting the things you care about. DetectionLab is a great place to run these types of tests. If you're an offensive security professional, you could use DetectionLab to see what sorts of forensic breadcrumbs you're leaving behind and what techniques are detected by commonly used tooling. DetectionLab is also a great learning environment. Many of the tools come pre-installed and pre-configured, so it's a great way to experiment with, test, and learn new tools. In the previous slide, I mentioned that one of the benefits of DetectionLab was that it could be deployed in many different ways. As of today, DetectionLab supports local deployment on VirtualBox, VMware Workstation and Fusion, Microsoft Hyper-V, and VMware ESXi. And as for the cloud, DetectionLab can be deployed to AWS and Azure. So, after that brief explanation, it's probably still worth answering the question, what problem does this actually solve? Or maybe if you're a bit more cynical, is this a solution for which there is no problem? A few years ago, shortly after I created DetectionLab, I was browsing Twitter and came across this tweet thread. This is basically the problem that I set out to solve. I wanted to make a quick and automated way for people to have an ADD environment to use for testing. This Twitter thread absolutely made my day. It made me really happy to see someone recommending something that I built. If you've ever taken the time to manually build an Active Directory lab environment before, you know how time-consuming it can be. Things get out of date, things break, updates accidentally get installed, and half the time you end up having to rebuild it after a few weeks anyway. However, most importantly, it's not a repeatable process. If you want a new lab environment, you're probably going to have to start over from scratch all over again. And some of the steps involved in doing this are finding the Windows ISOs, actually going through the installation process for all of the operating systems, creating the domain, installing software, creating GPOs. It's really time consuming and it's a lot of manual work. When I first started work on DetectionLab, I didn't actually know if it was going to be technically feasible. As I was researching methods for automating the creation of virtual machines, I started looking at tools called Packer and Vagrant because, based on what I was reading, they seemed like they might be capable of doing something at least similar to what I was trying to accomplish. The tooling wasn't a perfect fit at first, but I thought I might be able to make things work. I eventually came across a repo called ADFS2 hosted on Stefan Scherer's GitHub, and it provided the framework for what I was trying to do. Stefan had created a repository where multiple VMs were brought up at once using Vagrant, which is one of the tools I just mentioned. I can't take all the credit for the work on DetectionLab. It was definitely built on the backs of people smarter than I am. If you're not familiar with Packer and Vagrant, don't worry. Neither was I when I started this project. I'll do my best to explain them in simple terms. Packer is basically a way to automate the creation of a virtual machine. If you've ever used VMware or VirtualBox, you know you have to click through a bunch of prompts in the Windows installer. Packer automates all of that and is a great way to automate the customization of your Windows VM as well once it launches. For example, maybe you want to add or remove users, change some registry settings, etc. When Packer finally finishes running, the output it provides to you is called a box. And a box is literally just a compressed virtual machine image. But that is what Packer uses as sort of a file format for its output. Here's a visual representation of how this works in DetectionLab. We provide Packer with the operating system, ISOs, a JSON file that contains some variables, and some batch and PowerShell scripts. And it will do its thing, and when it's finished, it will provide us with a completely installed virtual machine, or what it calls a box, as output. After Packer has finished creating its boxes, we can then use Vagrant to launch and control those virtual machines. Vagrant is meant to provision host. The provisioning process occurs when the machine boots for the first time and is when most of the software and installation and configuration happens. It's also when the domain controller and Active Directory components get created. Vagrant uses what they call a Vagrant file, which is very similar to a Docker file, to control how the host gets provisioned. Once again, here's a visual representation of what's happening. Ultimately, once DetectionLab is finished building, it will consist of 4 different hosts. We are supplying Vagrant with 3 boxes, which you can basically just think of as base AMIs if you're familiar with AWS, and a collection of PowerShell and shell scripts. The Vagrant file tells Vagrant how and when to run those scripts and sets some basic parameters around the virtual machine configuration. Once Vagrant provisioning has completed, here's what we're left with. There are 4 total hosts in DetectionLab: Logger, DC, WEF, and Win10. Logger contains the majority of services, including Splunk, which is where all of the logs get centralized. DC is called DC because it's a domain controller. WEF is a Windows event collector that collects Windows event logs from all 3 of the Windows machines using custom subscriptions. Win10 runs Windows 10 to simulate what a user workstation might look like in this environment. In the previous slide, you may have seen some tool names you didn't recognize in the diagram. During this next part of the talk, I'll provide a quick overview of some of the primary tools that come pre-installed in DetectionLab and explain what their purpose is. Unfortunately, I won't have time to address each and every tool, but please visit the DetectionLab documentation website shown in this slide if you'd like to learn more about them. On the Logger host, which is the Ubuntu host, Splunk is installed and is pre-configured to collect and index a large amount of telemetry from the Windows hosts, including Sysmon, PowerShell, OSQuery, and Windows event logs. Although Splunk isn't an open source piece of software, I use it in DetectionLab because I personally think it is the most powerful and intuitive solution available. The apps and add-ons make onboarding data very easy, it supports alerting out of the box, and the initial trial license allows up to 500 megabytes per day of ingest. I've listed the index that are created as a part of DetectionLab on the right-hand side. Because I mentioned it in the last slide, it's worth mentioning that DetectionLab uses a custom set of Windows event subscriptions. By default, the telemetry provided by the security and system Windows event logs is inadequate for detecting a wide range of events and providing a detailed timeline of system activity. However, there are additional items that can be audited by Windows, and this repository contains a specific set of guidelines that is tailored to maximize the security relevant telemetry while filtering out noisy or unuseful Windows events. One of the greatest advantages of configuring Windows Event Forwarding or Collection is that it's built into Windows. You don't have to install an agent or any log forwarders like Beats or Splunk on every endpoint you want to collect logs from, because the Windows log collectors will centralize them for you. You can also define XML-based subscriptions to be extremely specific about the events you want to include or exclude. In DetectionLab, the WEF host, which is named that because of Windows Event Forwarding, plays the role of the Windows Event Collector. Events from all three Windows hosts will get centralized on the WEF host. These subscriptions and audit settings collect exponentially more data than the default Windows settings. WEF is not a widely known or implemented technology, but based on its flexibility and power, I believe it should be. Additionally, OSQuery is installed on each Windows host, and it is managed using a free open source tool called Fleet. Fleet provides a nice web UI and allows users to change the configuration settings and queries for OSQuery remotely using a centralized console. If you aren't already familiar with OSQuery, it basically exposes elements of the operating system as a database. By default, OSQuery runs as a daemon on a host, reads from a local configuration file, and logs to the file system. Everything is more or less done locally. However, OSQuery can also be configured to connect to it via TLS to an OSQuery manager, which can then dynamically supply new configurations and centralize log collections. By default, OSQuery is effectively a read-only tool. It's purposely designed to prevent arbitrary file contents from being viewed or code from being executed. For this reason, OSQuery is a very popular tool with privacy-conscious security teams. However, additional functionality can be added through the use of extensions. Fleet is what DetectionLab uses as an OSQuery manager. Fleet also allows queries to be issued on an ad hoc basis against hosts. One way this can come in handy is, say for example, you have a threat intelligence team, and that team receives some information that a specific Chrome extension has been discovered to be malicious and is sending malicious traffic. One thing that you could do is log into the Fleet console and using OSQuery on the back end, check all of the installed Chrome extensions across every host on your Fleet to determine very quickly if you have any hosts that have that malicious Chrome extension installed. This can be done in a matter of minutes, when I think this usually takes organizations in the matter of hours, if not days, to complete that sort of survey. The next tool to cover is called Velociraptor, and I think Velociraptor is my favorite tool of all of 2020. Like OSQuery, Velociraptor runs as an endpoint agent and can be controlled via a central web console. However, some of the biggest differences between Velociraptor and OSQuery is that Velociraptor can execute code on systems and has very powerful built-in forensics capabilities, such as the ability to parse the MFT, pull memory, do file system timelining, etc. I don't even think I'm scratching the surface of what's possible with Velociraptor on this slide, but I've been really impressed with it, and I encourage you to check out their GitHub page and website. The next tool to cover is Microsoft Advanced Threat Analytics, or ATA. According to Microsoft, ATA is an on-premises platform that helps protect your enterprise from multiple types of advanced targeted cyber attacks and insider threats. In DetectionLab, ATA is installed on the WEF host, and a lightweight gateway is installed on the domain controller. Microsoft ATA does a bit more behavioral analysis as opposed to this sort of file-based on-disk antivirus analysis, and is designed to identify commonly used tools and techniques to enumerate and exploit Active Directory. Although ATA is not open source, I think it's important for defensive security experts to know what sorts of techniques ATA is capable of detecting and how those techniques could potentially be bypassed. In the same vein, I think it's important for offensive security experts for the same reasons. Another excellent source of Windows endpoint telemetry is Sysmon. DetectionLab uses Sysmon in conjunction with Olaf Hartung's Sysmon modular configuration. Sysmon is a tool developed by sysinternals that is really great for collecting data like process creations, network connections, and file modifications. One thing I'm personally excited about is that according to Mark Rusinovich, in 2021, a Linux version of Sysmon is supposed to be released. I use Olaf Hartung's Sysmon config in DetectionLab because he's done an extensive amount of work fine-tuning the configuration to remove false positives, and the configuration gets updated consistently in the GitHub repo. In addition, he tests the config via a continuous integration pipeline. Personally, nothing warms my heart quite like security people testing things to ensure they work. On the Ubuntu-based Logger host, Zeek and Suricata are installed to help you monitor network traffic and create or test intrusion detection system rules. Both of these projects are open source and log their data to Splunk. Because these applications monitor network traffic, VirtualBox and VMware will prompt you to ask if you'd like to allow your network traffic to be monitored when you're building DetectionLab. Zeek provides deep introspection into network data, while Suricata is a successor or alternative, depending on who you ask, to Snort. Suricata has the ability to capture and analyze PCAPs, in addition to having an intrusion detection signature-based rules engine. Guacamole is a delicious food. However, in this case, it's also a project developed by the Apache Software Foundation that allows you to control a host over RDP using your browser. It's included DetectionLab purely to make controlling 4 separate virtual machines more convenient. If I had an unlimited amount of time, I would go into detail about every installed tool in DetectionLab, but for now, just know that there are additional tools installed in the C tools directory on all of the Windows hosts, and that more documentation on all of these tools is available on the DetectionLab website. Up until now, I've been telling you about what DetectionLab is. However, now I'd like to show you how it can actually be used. The point of this talk wasn't to show what DetectionLab was, but to show how it can be used to facilitate or simulate real-world triage and analysis. Let's start off with a scenario many of us are probably familiar with. An adversary has gained a foothold on our network and has run Mimikatz against a host somewhere. So, what do we know about Mimikatz? Attackers often use it to recover plaintext credentials or hashed passwords from systems. It's become very popular since its release and is basically ubiquitous in terms of being in an attacker's toolset. Mitigations have since been introduced in Windows to prevent the exposure of plaintext passwords, in Windows 10 for example. However, some of those mitigations can be bypassed. For the sake of this scenario, let's assume we don't know any of the malicious file names being used. Let's also assume the adversary has modified Mimikatz in such a way that it avoids detection by antivirus. Lastly, to mix things up a little bit, let's say our intrepid defenders have gone ahead and done extra credit and enabled LSA protection. This protection makes LSAS a protected process, which means that programs that want to read its memory or inject memory into it must have a valid code signature. Before I go any further ahead, I have to talk about one of my favorite projects of all time, JP-CERT's tool analysis results. If you aren't familiar with this research project, basically JP-CERT set up an environment where they installed Sysmon and enabled advanced event log auditing on Windows. And then they went ahead and ran a bunch of really well-known offensive security tools or just purely malicious tools in that lab environment. And as they ran those different tools, they recorded the event logs and Sysmon events that were generated by running those tools. This research project is an excellent reference, and honestly, it almost makes my talk irrelevant. Here in this screenshot, we can see Sysmon detecting Mimikatz via the process access task category. Specifically, Mimikatz is attempting to access lsas.exe. Additionally, the Windows event log shows a handle to an object was requested, and if you look further into that event, the handle is to read process memory from lsas.exe. So now, ahead of time, we already know what the Sysmon and Windows event artifacts are, but I think there's probably some other ways that we can detect this, and I think we can do it using DetectionLab. So let me show you how it's done. We log into Splunk, we search across all the indexes for mimikatz.exe. Just kidding, that would be completely cheating. We can never expect that we'll know the names of malicious files, and plus, that's definitely not a robust way to build a detection. So let's walk through the steps our adversary took one at a time. Start from the beginning and replay the actual attack. While the adversary had a foothold on one of our systems, they uploaded Mimikatz, which they had renamed to sysconfig.exe, and they use it and attempt to dump credentials from all available authentication providers using the logon passwords command. However, this request is denied by the operating system. Specifically, the request to access LSAS's program memory is denied. As we had mentioned earlier, our defenders had enabled LSA protection. However, our attacker, not stopped so easily, learns that Mimikatz has an accompanying driver that it can load called MimiDrive. So they go ahead and load the driver. One capability of this driver is that it allows our adversary to unprotect processes that have previously been protected. So our adversary goes ahead and unprotects lsas.exe, which effectively undoes the work we had done by implementing LSA protection. Once again, they run the logon passwords command to attempt to try to dump clear text passwords. This time, there is no error message that they receive, but they also aren't able to see any plaintext credentials. Our persistent adversary does some reading across Microsoft's documentation and learns that by setting the use logon credential for the wdigest authentication package to 1, they can force those plaintext credentials to be stored in the memory of lsas.exe. After our poor victim logs onto the machine again, our adversary reruns Mimikatz and is then able to recover the plaintext password for the vagrant user, which in this case the password is also vagrant. So now it's time to switch sides and let's sit in the seat of a defensive security professional. We already know to avoid anything related to file names, but what are some other ways we could potentially detect this sort of activity? I like to think of building detections as laying a minefield. The goal is to use the wide array of data and telemetry available to you to force our attacker to move slowly and in a constrained manner. One wrong technique or command could lead to the end of our adversary's operation if we have sufficient telemetry and a capable incident response team. So one way we could do this is to monitor sensitive registry keys. There are dozens, if not hundreds, of Windows registry keys that may be of interest to an adversary. Some of these keys disable security protections or enable features such as wdigest storing credentials in memory that weaken security. Construct a list of keys that are worth monitoring and investigate when a system's registry deviates from the expected value. Even better, you could use a GPO to change the value back to the secure value and log if a registry key has detected to have been changed at some point. Surprisingly, monitoring registry keys is not a feature that many security tools include. One way that you can monitor registry keys in DetectionLab is by using osquery and Fleet. In this screenshot, which I hope you can read, we are able to construct a SQL query to periodically monitor the contents of the wdigest useLogon credential key. We know that key shouldn't even exist by default, but if it does, and it has a value of 1, we should alert on that unexpected behavior. You don't have to use osquery for this, but you can. As defenders, we know that by enabling LSA protection, the only known way for an adversary to defeat that protection is to install a kernel driver. Therefore, we should be monitoring our event logs for any kernel drivers being installed onto any endpoints. Because the Windows event log doesn't supply the file hash or details about the driver, we can use other tools that we have at our disposal, like osquery or Velociraptor, to do additional analysis of the file and see if that's a driver that we would expect to be loaded into a system. It's worth noting that although LSA protection was bypassed, we still had the benefit of forcing the attacker to install a system driver, which is inherently going to be noisy and something that we're able to detect. This was not a total loss. I mentioned earlier that I believe building detections around file names is weak and not robust. However, one thing that's similar that I think can be extremely useful is monitoring for malicious program parameters. I would never expect to see the string securl_sa in any legitimate log file in an Active Directory environment, and I would consider setting up alerts for these unique parameters that are unique to the tools that they're fed to. Sure, this is completely bypassable if the adversary modifies the parameter names in the program ahead of time, but that's just one more mine in our field and just one more step that the adversary has to take to be successful for operating in our environment. If you wanted to go for extra credit, you could scan actively running processes or processes that exist in certain directories using Yara. The Windows version of osquery recently introduced this feature, and the query below shows the results of running a Yara rule that looks for Mimikatz against all of the running processes on a system. Using osquery, you can load up any Yara rules you'd like, and you can run them against any processes or any files on disk. Alrighty, so we've covered the Mimikatz scenario. Let's see if we have time to do one more about process injection. Why do adversaries use process injection? The simple answer is that it helps them disguise their activity. If an adversary launches malicious commands under the context of legitimate process, defenders are less likely to notice it as an outlier or unusual activity. However, it's worth noting that sometimes legitimate processes do this as well. Debuggers are a great example of legitimate programs that use process injection. The 1-minute explanation of one method of process injection is a target process is selected, memory is then allocated in that process, a DLL or code is written to that allocation, and then that code can be executed by the use of a function such as create remote thread. This is a very common way that process injection is achieved. This is obviously a way oversimplified explanation, but this topic alone is enough for a talk all in itself. As it turns out, process injection is also very common. So common, in fact, that Red Canary said it was its most commonly observed TTP. Ransomware crews have recently been leveraging a tool called Cobalt Strike, which also uses this technique. So, for this scenario, let's assume we have a host that's been affected by malicious process injection. In this scenario, our adversary is using Metasploit Meterpreter to execute commands on a target system. They use the migrate command, which allows them to relocate the Meterpreter code from one process to another using process injection. Our adversary selects a process with a process ID of 956, which is a legitimate Windows process, and now is running a Meterpreter under that process's context. If we wanted to detect process injection, here's some things we could do. We could pull memory images from a bunch of different hosts and analyze them using an open source tool like Volatility or other memory analysis tool. However, for the most part, this really doesn't scale well. Collecting and analyzing hundreds or thousands of memory images takes an impressive amount of infrastructure, both for the storage and analysis. If we have an EDR agent already installed, it's possible that it may have been able to detect this activity already. However, many organizations do not because they either can't afford EDR or they lack the expertise to derive value from it. So my solution here is to start what's called a hunt using Velociraptor. Velociraptor is free and open source, so it should be accessible to most people. I have to caveat this next slide by giving credit to Eric Capuano for the inspiration for this technique. I highly recommend watching the video linked in this slide. Moving on, we'll open the Velociraptor console and use the Hunt Manager feature. We'll create a new hunt and select Windows System PowerShell as the artifact. This artifact will allow us to run arbitrary PowerShell against our own endpoints. The command shown in the previous slide below downloads a script authored by Jared Atkinson, which uses PowerShell to look for evidence of process injection in running processes. After downloading the script, it imports the function into PowerShell and runs it. After the script completes running across all three of our Windows hosts, we can view the results in the form of a notebook in the Velociraptor console. This notebook shows us the standard error and standard out from the PowerShell command that we ran. Here, you'll notice that only a single host, Win10, has standard output listed. In this standard out, we can see that getInjectedThread, which is the function we ran, listed a process with a PID of 956, which, if you remember, is the process that the interpreter was migrated into. Process ID 956 is logonui.exe, which is a legitimate Windows process. More importantly, getInjectedThread even shows us the exact time that the injected code was executed. Knowing the time that the thread was executed helps us develop a time frame for the incident and set parameters around other artifact collections. To continue this investigation, we could use Velociraptor to download event logs and search through data near that time frame to look for unusual activity. We could download an entire memory image to see what exactly was injected into the process. This process could also help us write YARA rules to detect further compromise in our environment. We could also download the NTFS master file table to observe file system activity near that time. Using Velociraptor, we can do this all from a single place in easily less than an hour. So, in conclusion, DetectionLab exists to help you save time by automating the boring stuff. The environment you create using DetectionLab is easy to destroy and recreate, which is a primary benefit of having infrastructure as code. I recommend using DetectionLab to learn how to use a variety of popular different defensive tools. If there are tools that you've seen today that maybe you're not familiar with, DetectionLab is a great environment to play around with them and get some real-world experience using them. If you are a DevOps professional, for example, maybe DetectionLab might be useful to learn how to configure and automate some elements of a lab environment. Lastly, if you are a detection engineer, use DetectionLab to find different ways to detect malicious activity. Also know that DetectionLab is customizable. These VMs can be modified to include or exclude whichever software that you prefer. If you would like just a stripped down Active Directory, that's a very easy change to make. If there are some programs you would like to add to DetectionLab on your own, that should probably just be a few lines of code. If you wanted to, you could even change DetectionLab to add additional VMs to build a bigger network. If you're interested in contributing to DetectionLab, please feel free to contribute features, fixes, or issues, and do that by visiting our GitHub. Feedback is always welcome as well. I can be reached on Twitter via @Centurion or @DetectionLab. I'd also like to take a moment to thank the JSAC committee and staff for hosting this conference and to all of the people who sponsor DetectionLab and make ongoing development possible. Hopefully by 2022, life becomes a bit more simple and I'll be able to meet all of you in person. Thank you so much. At this point in time, I am happy to take any questions in the Slack channel.